Hello, ladies and gentlemen. Today we will be learning about partial fraction decomposition. So before we can really dig deep into that, we're going to start off with a warm-up problem. So the warm-up problem is going to, here it is, ask you to add or combine the two rational expressions. So I just want you to take a minute and determine what you get when you add these two rational expressions. Okay, hopefully when you did that, you got the answer that I showed you on the Ed puzzle. So now we're going to talk about actually what partial fraction decomposition is. So partial fraction decomposition is the process of starting with the simplified answer and then taking it back apart or decomposing the final expression into its initial polynomial fraction. So figuring out what the rational expressions were that gave you that final answer. There are actually four methods for this. We're going to focus on two of them today, and then tomorrow we will see the next two. So the first two that we're going to talk about are called non-repeated linear factors, so that's over here, and then repeated linear factors. So I want you to look at the examples, and we're going to just see if you can figure out what's going on with the examples and what makes the ones on the left different than the ones on the right. So hopefully you notice the ones on the left, they actually have just one term in the denominator or one factor in the denominator that is not raised to a power. So there's this factor of x, so that's one factor, and then the factor of x plus 3. Those are linear factors, but they're not repeated. Same thing with this. I have x plus 1, and I have x plus 3, and those factors are not repeated. Versus over here on the right-hand side, so we have these repeated linear factors. So here I have my first factor of x plus 1, but because it's raised to the second power, we would say that this factor is repeated. It's like x plus 1 times x plus 1. The same thing here, we have x plus 2, but it is actually to the first power. So this x plus 2 actually falls into this category. So this problem actually has two different types of factors, a repeated and a non-repeated linear factor. The same thing with this example over here. So my non-repeated linear factor is just x to the first, and then my repeated linear factor is x plus 1 squared. So we're going to learn procedures on how to break these things apart or to decompose them into their original fractions that created this one rational expression. So the first one will be for non-repeated linear factors, and there are 5 steps to this. Each step is pretty basic until you kind of get to the last step, and that's where all the work occurs. So the first thing that you need to do is just to make sure that the numerator's power is less than the denominator's power. If that isn't the case, we're going to learn a way to make that be the case. But if that's not happening, you can't do this process. The second step would then be, if it's not already done for you, you actually want to factor the denominator. Sometimes it'll already be factored, but if it is not, you want to do that in step 2. Step 3, you're going to create fractions or separate into fractions, and you'll create one fraction for each factor in the denominator, and a constant will then go in the numerator for those fractions. So again, you're going to create these fractions. You're going to have one fraction for each of the factors in the denominator, and then in the numerator there will be a constant. Step 4 will be to multiply by the common denominator to remove or eliminate the fraction. So you want to get rid of the fractions in step 4. And finally, step 5 is where all the work is occurring, and you're going to do some solving for each constant. And there's a couple of ways to go about solving, and I'm going to try and show you at least one of them today, maybe both of them if we can have time with our 15-minute video. Okay, so let's see an example of non-repeated linear factors. So here's the first example. So it's 5x plus 1 over x squared minus x minus 12. Step 1 was to make sure the numerator's power was less than the denominator's power, which it is, so I don't even have to worry about step 1. Step 2 was to factor the denominator. So when we factor the denominator, we get 5x plus 1 over x plus 3 times x minus 4. So what I have are two linear factors that are not repeated. So linear because it's x to the first power, and then non-repeated because the factor itself is raised to the first power. Okay, so the third step then is to take and write the factored version of the expression into separate fractions with constants in the numerator. So I take my x plus 3 term and write it with a constant above it, and I take my x minus 4 term and write it with a constant above it in the numerator. If there were more factors, I would have more fractions. So if I had another like x plus 2 over here, then I'd have another fraction over here. The constants that we use can be anything you want. A and B tend to be the most common ones they use, sometimes C or D, depending on how many factors we have. So I've separated into my fractions. Now my fourth step is when we multiply to get rid of the fractions. So I am multiplying, or I multiplied, I should say, by the common denominator of x plus 3 times x minus 4. So I end up with 5x plus 1 on the left. My a in the numerator gets multiplied by x minus 4, so the x plus 3 cancel. And the b value here gets multiplied by x plus 3 because the x minus 4's cancel. So here's the equation that I have. I'm going to go ahead and expand this so that I have it all multiplied out, so it's distributed. So then here's where kind of the big aha moment has to happen. So you have to understand at this point in time that when you have an equation, whatever happens on the left side has to be equivalent on the right side. So for instance, on the left side, I have this 5x on the left, which means that any term on the right-hand side that has an x would have to combine, they would have to combine together to give me 5x. So for instance, right here I have 5x, and then I have ax, and I have bx. So these two on the right, have to equal this 5x on the left. And the same is true for these constant terms. So I have a 1 on the left, I have this negative 4a on the right, it's a constant, and a positive 3b also on the right, and it's a constant. So I'm going to take this information and I'm going to write it as a system of equations. So let's just go this way. So the system of equations that I create were the a in front of the x, the b in front of the x, and the 5 in front of the x. So a plus b equals 5. Then I'm taking the negative 4a constant, the positive 3b constant, and that equals the constant of 1. So from here, I can choose to solve the system equations in whatever manner I want, whether it is substitution or elimination, whatever works best for you. So it looks like what I decided to do, let's not uncover the whole thing, was to use elimination. So I multiplied the top equation by 4, combine them to give us a b value of 7b equal to 21, which means b equals 3. And then once you get the b equal to 3, then you're of course going to substitute that 3 back in over here to get a equal to 2. So then the final thing you need to do to really make this be correct is you need to take these two values and fill them into the decomposed equation. So you really need to, see where I'm at right here, rewrite this so I have 2 in the numerator and x plus 3 in the denominator. This doesn't look so hot, sorry. And then the b fraction is 3 in the numerator and x minus 4 in the denominator. And this is actually the final answer to the decomposed fraction. So 2 over x plus 3 plus 3 over x minus 4. Okay, we still need to see the other type of method. So this is when you have repeated linear factors. The steps are nearly the same, so I'm going to try to go through them a little bit faster this time. So step 1, same thing. The numerator's power must be less than the denominator's power. Step 2, same as before. If it's not already done, you want to factor the denominator. Step 3 is where it gets a little bit different. So you're going to separate into fractions again, and there will be a fraction for each factor in the denominator and still a constant in the numerator. There'll still only be constants in the numerator here. But then you need to have an additional fraction if the factor is repeated. So however many times it's repeated will actually give you that many additional fractions. Okay, so we're going to see that. That step is, I think, where it's the most confusing. So we'll focus on that when we do the practice problem. And then step 4 is the same, multiply to remove the fractions, so just like before. And step 5 is the same as well, solve for each constant. So everything is the same except for this little step in here where it is creating the different fractions with the constants in the numerator. So let's go ahead and see the example problem. So here's my example problem. I did go ahead and give you something that was already factored for you. So you actually have step 1 done because the numerator's power is less than the combined denominator's power. So x squared times x to the first is x cubed. So x squared is less than x cubed. Done. Step 2 is to factor the denominator. Well, that's already done for you, so you don't have to worry about it. Step 3 is where that weird step is occurring where you need to create fractions. So you're going to create 3 fractions for this. One for the x term, one for the x squared term, and one for the x plus 2 term. So here's what it will look like. So you keep the original here. That should equal something that has 3 fractions, an a, a b, and a c. So this term is just if you hadn't repeated the x, so it's a over x. Oops. Now you have to think, well, it could have also been x squared fraction, so we have b over x squared. And then the last one is c over that last non-repeated factor of x plus 2. Okay, so I have my fraction set up. And then step 4, just like before, it's really like cross multiplying. You're multiplying by the common denominator to clear the fractions. So the first fraction is completely gone, 5x squared plus 3x minus 2. My a over x fraction, the x will get canceled out, but then I have another x from here. So I end up multiplying by an additional x and an x plus 2. My b needs just the x plus 2, and the c needs an x squared. Okay, so here's where I'm at now with this. This looks kind of messy to go ahead and multiply out. But instead of multiplying it out, I'm going to show you another method, which I think works just as well. So what you do is you let x equal 0, because if you let x equal 0, that takes the a term away here, it takes the c term away here, allows you to solve for b. You can also let x equal -2, because if you do that, that allows you to get rid of the b term and the a term and solve for c. So that is the goal that we're aiming for right here. So we're going to start by letting x equal 0. You have to substitute 0 in for x on both the left and on the right hand side. Okay, so when we do that, we get -2 on the left, 0, 0, -2. We get a 0 here, we get a 2 here, and then a 0 here. So that we actually find out that b is equal to -1. Great, we have b. All right, so now let's go ahead and let x equal -2, because again, that's going to get rid of this part and this part. So when we do that, we get a little bit harder, but we get 20 for this part, -6 here, and still the -2. This a part becomes 0, the b part becomes 0, and I can solve for c by getting 4c, and I end up with c equal to 3 after I solve all of the information here. Now I still have to do a little bit more work. I'm going to go ahead and distribute this whole entire equation on the right-hand side up here from step 4. But when I do that, I'm going to use the -1 for b and the 3 for c. So that way I can just figure out what pieces of information I need to set equal to find a. Once you get good at this, you probably won't even need to do this step. If you start to figure out the pieces of this, there's less steps you actually need to take. Okay, so I substituted, I distributed. So I have ax squared plus 2ax. And then if b is -1, I get -x. And then -2 when I distribute. And then again, if c is 3, I have 3x squared. So then all I did is I took out the information just like I did on the last problem, where I know that the a term that's here is next to the x squared. So that has to equal all the other x squared terms in the problem. So there's a 5 over on the left, an a and a 3 on the right. So I did 5 equals a plus 3. So I could solve for a, and I get a equals 2. You could have also said, well, there's a 2a here with the x. There's a 3 over here, and there's a -1 in front of this x, and then 3 equals 2a minus 1, and solve for a that way as well. Now you can take the a term, put it in its spot in the first fraction, take the b term of -1 and put it in its spot in the fraction, and take the c term and put it in its spot over its fraction or in its numerator, And this is the decomposed fraction that we get. I would highly recommend